Okay, hi everyone. We're going to continue our solution of second order constant coefficient homogeneous equations by looking at another case. And in this is what we call case 2. And it is when the characteristic equation has two complex conjugate roots. So remember, we started off with our equation ay double prime plus by prime plus cy equals 0. We guessed the solution of the form y is equal to lambda x. And then we got the characteristic equation a lambda squared plus b lambda plus c equals 0, which we recognize as a quadratic equation with the solution minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and so last time we did the case where the discriminant was positive, and so you got two real distinct roots. And in this case, we're looking at the case, in this video, we're looking at the case where b squared minus 4ac is negative, and so you get two complex conjugate roots. That is, let me call them lambda plus minus, and that is equal to alpha plus or minus I beta, okay? The plus with the plus and the minus with the minus. And you can write down exactly what that is. Alpha is equal to minus b over 2a, and beta is, because b squared minus 4ac is negative, 4ac minus b squared is positive, and so we will write that, and there's an I here, so beta is the square root of 4ac minus b squared over 2a. Okay. All right, and so now we want to know how you write down the solutions. We need two linearly independent solutions, which means that one is not a multiple of the other, and they're both going to be of this form. So that means y1 is e to the alpha plus I beta times x, and y2 is e to the alpha minus I beta times x, which notice I can write as e to the alpha times e to the I beta x. And this one is similarly e to, oops, I left off the x there, sorry. E to the alpha x, e to the minus I beta x. Okay. All right, so those are two linearly independent solutions. So one perfectly good way to write it, although many books at this level object to it, is to say the general solution in this case is y of x is c1. Notice there's going to be, okay, let me just write it out. E to the alpha x, e to the I beta x, plus c2 e to the alpha x, e to the minus I beta x. And notice there's an alpha, e to the alpha x in both. So you can write it as y of x is e to the alpha x times c1 e to the I beta x plus c2 e to the minus I beta x. Okay, and that's one perfectly good way to write out the general solution of our second order constant coefficient homogeneous ODE in this case. Now, why do people not like that? And why don't you see that in my books at this level? And that's because you have a complex valued function here. E to the I beta x is a complex valued function. And in general, at this level, people like to have real valued functions. So we got to do a little playing around with that to get it so that we can write it as the sum of two real valued functions. Okay, so this is where we'll pull on what you learned in the review video, which hopefully was just a review for you, that you can write e to the I beta x as cosine beta x plus I sine beta x. And e to the minus I beta x is cosine beta x plus I sine minus, well, this should be minus beta x, sorry, plus I sine minus beta x, except that cosine is an even function and sine is an odd function. So this becomes cosine beta x minus I sine beta x, using the fact that cosine is even and sine is odd. Okay, so notice that by playing around with things, you can write cosine beta x. Add these two equations and then divide by 2, because you'll get a cosine I beta x plus a cosine I beta x, so that's 2 cosine I beta x, and that'll be, and the sine terms cancel out, and so you get e to the I beta x plus e to the minus I beta x divided by 2. Okay. So in other words, you can write cosine beta x as a linear combination of e to the I beta x and e to the minus I beta x. And now by playing the same game with sine, so subtract the second equation from the first and divide by 2i, you will get sine beta x is e to the I beta x minus e to the minus I beta x divided by 2i. Okay. So you can also write sine as a linear combination of these two complex exponentials, but you have to allow for complex numbers. That's okay. We're fine with allowing for complex numbers. There's no problem with that. So in other words, instead of writing my solution in terms of the two complex exponential valued functions, by changing the values of the constants, I can write that solution, and so that I can write that solution as y of x is e to the alpha x times, let me call it capital C1 cosine beta x plus capital C2 sine beta x. And you can sit there and figure out exactly what capital C1 and capital C2 are in terms of little c1 and little c2, but we really don't need to know that. You're going to decide when you're doing a problem whether you prefer to do it in one form where you have complex valued functions or the other where you have real valued functions. And I know for most of you engineers, they're going to want you to write it in terms of sines and cosines. So now let's take a second and look at an example.